For this screencast of chapter 19, I have chosen a problem from the book which uses loop rule and node rule to determine the current in a circuit. And the problem number is 70, and the problem is the figure below consists of two flashlight batteries and two nichrome wires of different length and different thickness. You can see the figure two batteries are connected by a nichrome wire, thin nichrome wire and thick nichrome wire. And it says the thin wire is 50 centimeter long and its diameter is 0.25 millimeter. The thick wire is 15 centimeter long and has a diameter of 0.35 millimeter. So the number A says the EMF of each flashlight battery is 1.5 volts. So determine the steady state electric field inside each nichrome wire. And the problem says to remember that in a steady state satisfies both node rule and energy conservation. So let me change the units so that we don't have a problem while doing the calculation. So the length of thin nichrome wire L1 equals 0.5 meter, length of thick nichrome wire L2 equals 0.15 meter. The diameter of thin wire D1 equals 0.25 millimeter, and diameter of thick wire D2 equals 0.35 millimeter. So before we get into the calculation, let me get some equation, just a revision from what we learned in chapter 19. It says the current in the wire depends on the cross-sectional area A of wire and average drift speed V. So the current in metal wire can be expressed as I equals NAV. Let us suppose that to be equation 1. The average drift speed of the mobile electron is proportional to the magnitude of electric field E, and that can be given by B equals UE. Question 2, where U is the proportionality constant called electron mobility. So now using the equation 1 and 2, we can get a relation of I equals and AUE to the equation number 3. So now coming back to the problem, we can get the area of thin wire A1 to be pi r square, where r can be written as d1 by 2, and putting the value given, it comes out to be 0.3925 into 10 to the power minus 6 meter square. You need to be really careful about the units over here, because if you do something wrong with the units, then the value will be different. So the area of thick wire A2 equals pi d2 by 2 whole r square, which comes out to be 0.5495 into 10 to the power minus 6 meter square. And since the batteries are connected in series, the total EMF of circuit equals 3 volt. So now using the node rule from Kirchhoff law in steady state, which says the current in thick and thin wire must be equal, that is I1 must be equal to I2, then NA1 UE1 equals NA2 UE2. So U and N gets cancel out, and we can get the relationship A2 equals A1 by A2 E multiplied by E1 to be the equation 4. And now we use the loop rule, which says the total potential difference is 0. That is, for this figure, total EMF minus E1 L1 minus E2 L2 equals to be 0. So we know the total EMF equals 3 volt equals E1 L1 plus E2 L2, and we have a relationship from equation 4, and putting that equation E1 L1 plus A by A2 E1 L2. So now we can get this relationship. So we can get the E1 to be 3 volt divided by this equation, and after we substitute with the value is given, it comes out to be 5.20 volt per meter. So the electric field of the thin wire is 5.20 volt per meter. So now we can use this E1 in equation 4 and get the value for E2, and after putting the value, it comes out to be 2.65 volt per meter. And the number problem number B says the electron mobility in room temperature of nichrome is 7 to 10 to the power minus 5 meter per second per Newton per coulomb, so that it takes an electron 36 minutes to drift through the 2 nichrome wire from location B to A. Here you can see the figure, and we need to find how much it takes from the electron to drift from B to A. So the average drift speed of electron in thin wire can be given by B1 equals U E1. This comes out to be 3.6 into 10 to the power minus 4 meter per second. So again, you need to be really careful about the units while doing this type of calculation. Similarly, the average drift speed of electron in the thick wire can be given by B2 equals U E2, which comes out to be 1.9 10 to the power minus 4 meter per second. So the total time that electron takes to drift the nichrome wire from B to A can be given by T equals distance taken by time, distance by velocity, which can be given by L1 by V1 plus L2 by V2, and putting our value comes to be 36 minutes, and thus we can show that it takes electron 36 minutes to drift through the nichrome wire from location B to A. And lastly, number C says there are about 9 into 10 to the power 8 mobile electron per cubic meter in nichrome. How many electrons cross the junction between the two wires every second? So the number of electrons crossing the junction in every second can be given by I1 equals n AV1, and we already have the value of n, which is 9 into 10 to the power 28 electron per meter cube. A, the area, which comes out to be 0.3925 into 10 to the power minus 6, and the V1 that we got earlier, 3.6 into 10 to the power minus 4 meter per second. And doing so, we get a value of 1.6 into 10 to the power 18 electron per second. So it says that the electron passing through the thin wire comes to be 1.6 into 10 to the power 18 electron per second, and this value is same as in the thick wire due to the steady state. Thanks.